Hello everyone, I'm presenting HFedATM, Hierarchical Federated Domain Generalization, via optimal transport and regularized mean aggregation. Our goal is simple. In hierarchical federated learning, where clients connect to stations and then to a cloud server, we want the final model to generalize to domains it has never seen, without sharing raw data. Federated learning protects privacy because clients train locally and only send model updates. But when the number of clients grows, a single server becomes a bottleneck. Hierarchical federated learning addresses this by adding intermediate stations. However, domain shift remains. A model trained on one group of clients may fail on a new hospital, camera, location, or text category. Existing federated domain generalization methods mostly focus on single server FL, so their behavior in the hierarchical setting is still underexplored. We define this setting as Hierarchical Federated Domain Generalization, or HFedDG. Clients are grouped under stations. Stations aggregate client models, and the cloud server aggregates station models. The target domain is unseen during training. The challenge is that stations do not have raw data, so the server cannot retrain or fine-tune on station data. It needs a data-free aggregation method that reduces mismatch between station models. Our analysis shows that target domain error can be decomposed into client-level risks, interstation divergence, and interstation divergence. Local HFeDG methods can reduce the client level and within station terms, but a gap often remains between stations. This explains why naive weight averaging can be suboptimal. Even if each station learns useful features, their models may not be aligned in the same parameter space. HFedATM directly targets this interstation gap with two components. First, filter-wise optimal transport, or FOT, aligns convolutional filters across station models. Filter indices are arbitrary. Filter number 1 in one station may correspond to filter number 10 in another. FOT matches semantically similar filters to the same index. Second, Shrinkage-aware Regularized Mean, or RegMean, merges linear layers using activation gram matrices instead of pure parameter averaging. Together, FOT handles convolutional layers, and RegMean handles linear layers in an aligned feature space. A key advantage is that HFedATM does not require raw client data. Clients only compute gram matrices from activations during the final forward pass, and stations aggregate these matrices before sending them to the server. The server then performs model merging. This makes HFedATM a plug-in aggregation layer on top of existing client-side algorithms. We evaluate HFedATM on vision and NLP benchmarks, including PACS, Office Home, Terra Inc., and Amazon Reviews. We attach HFedATM to FedAverage, FedProx, FedSR, and FedIIR. Across different heterogeneity settings, HFedATM consistently improves these baselines. The gains are especially strong with FedDG methods such as FedSR and FedIIR because they reduce local domain shift and allow HFedATM to close the remaining interstation gap. HFedATM also outperforms recent hierarchical FL methods such as MTGC and FedRC while remaining data-free and simple. The ablation study confirms that both components matter. Removing FOT hurts performance because filters are no longer semantically aligned. Removing RegMean also hurts because linear layers are merged without considering activation geometry. We further test privacy and efficiency. HFedATM remains stable under differential privacy noise, adds less than 10% training latency per communication round, and adds only modest server memory. In summary, HFedATM introduces the HFedDG setting, provides a hierarchical generalization analysis, and proposes a practical data-free aggregation method. By aligning convolutional filters and merging linear layers with RegMean, it improves generalization to unseen domains while keeping privacy and efficiency suitable for real hierarchical federated learning deployments. Thank you.